first glance, it seems impossible to heat the glass of water by using the ice cubes. Moving heat from ice to water violates a fundamental rule used every day in heating and cooling equipment. That rule says heat always moves from warmer to cooler things. Moving heat the other direction is not easy, unless we use a heat pump to do it. Extracting heat from cooler things, namely the cold outside air of winter, and moving it to warmer things, the inside of our homes, is the job done by a heat pump, and it does it very efficiently. The heat pump violates no laws of physics. Heat still always moves from warmer objects to cooler objects. Surprisingly, the thing the heat pump uses to move the heat is, right now, even colder than either the water or the ice. It is refrigerant. The same refrigerant that, in summer, is used by an air conditioner to take heat out of the air inside our homes and move it outside. In winter, the heat pump uses the refrigerant to move heat in the opposite direction. Heat is taken from outside to heat the inside of the home. The heat pump does it by reversing the work of the air conditioner's indoor and outdoor coils. In its simplest form, the heat pump is a reverse cycle air conditioner with some very important components added. An air conditioner cools by boiling refrigerant under low pressure. The heat necessary for the boiling comes from the warm air passing over the indoor evaporator. The refrigerant then gives up the heat to the outdoor air at the condenser. The inside of the home is cooled and, in a sense, the outside of the home is warmed. Reverse the two coils and the inside of the home is heated, using heat taken from the air outside the home. Even if that air is well below freezing, no matter how cold the outside air gets, it still contains some heat. The heat pump's job is to extract as much of this heat as it can and discharge it to the inside of the home. A heat pump uses the same principles as an air conditioner, except the evaporator is in a temperature that is already cold. The condenser, on the other hand, is indoors, where the ambient is at a lower than normal condensing temperature. A heat pump operating with the indoor coil as a condenser typically has a condensing pressure of about 210 pounds per square inch. For R22, this is a coil temperature of about 105 degrees Fahrenheit. Return air temperature is normally between 65 and 75 degrees. Outside the home, for an ambient temperature of 40 degrees, the evaporator operates at about 44 pounds per square inch. With 40-degree air moving over the condenser, coil temperature is about 21 degrees. The temperature difference across the outdoor coil is about 19 degrees. Under these operating conditions, the outdoor coil absorbs approximately 70 BTUs of heat for every pound of refrigerant that passes through it. Even though the outdoor air temperature is at 40 degrees, it contains more than enough heat to support boiling of the refrigerant. For a 3-ton heat pump, the refrigerant flow rate is about 520 pounds per hour. The heat extracted at the outdoor coil every hour is approximately the 36,000 BTUs needed to heat the home. The heat pump has accomplished its impossible job, moving heat from a cooler location to one that is warmer. And it will do it with an efficiency that also appears impossible. In a high-efficiency design, a 3-ton heat pump uses about 4 kilowatts of electricity to move 36,000 BTUs of heat. 4 kilowatts is equivalent to about 13,000 BTUs. That means for every 1 BTU of electrical energy showing up on the electric bill, the homeowner gets almost 3 BTUs of heat. The value of the heat pump is quickly seen. This ratio of heat energy output to electrical energy input is called the coefficient of performance, often referred to as the COP of the heat pump. COPs above 3 are available in higher efficiency heat pumps. Straight electric heating furnaces, on the other hand, always have a COP of 1. For 1 kilowatt of electricity in, there is 1 kilowatt of heat energy out. This high improvement in energy use is a major reason for the success of heat pumps in many applications. Reversing the job of the two coils in an air conditioner to convert it to a heat pump is not a simple task. At one point in the early history of the heat pump, the reversing of the coils was done by physically moving the two coils. Needless to say, this approach did not last very long. The universal method used today to reverse the job of the two coils is to use a four-way solenoid valve, or as it is more commonly known, a reversing valve. Reversing valves control the function of the indoor and the outdoor coil by redirecting the flow of the compressor piping. All reversing valves have an inlet from the discharge of the compressor and a suction connection to the compressor. Two additional tubes connect to the indoor and the outdoor coils. The reversing valve does its repiping job using an internal slide which can move to one of two positions to direct compressor flow. The slide can move to the heating position where the indoor coil is connected to the discharge of the compressor. This makes the indoor coil the condensing coil. The outdoor coil is connected to the suction side of the compressor, making it the evaporator. In cooling, the slide is moved to the opposite end of the valve body. The indoor coil is connected to the suction side of the compressor. The outdoor coil is connected to the discharge of the compressor. Evaporator and condenser are connected for cooling. The force